Today's webinar is Liquid Sample Introduction for ICP-AES, presented by Fred Smith, Product Line Technical Manager for Liquid Products for Teledyne CETAC. This webinar is being recorded and will be available within a few days. You will receive an email notification of its availability. Okay, now I'm going to turn it over to our
and for taking time out of your day to attend our webinar. The topic we're going to discuss is the measurement of element impurities in a higher daily dose drug product using the criteria specified in USP 232-233. And for these tests, we're going to describe the use of an ultrasonic nebulizer with ICP-AES detection. So we'll move to our first slide and go through a little bit of introduction information about USP 232 and 233. On January 1st in 2018, the U.S. Pharmacopoeia enacted new criteria for element impurities in finished drug products. These criteria, detailed in the USP Register 232-233, now recommends analysis of drug products for element impurities by either inductively coupled plasma atomic emission spectroscopy, ICP-AES, or inductively coupled plasma mass spectrometry, ICP-MS. Previously, element impurities had been evaluated by older and established wet chemistry techniques, but now instrumental techniques by USP 232-233 are the recommended analysis types to use. So laboratories must measure these impurities based on what is called a J value for each drug product. So drug products, of course, can be oral, parenteral, meaning intravenous injection, or inhalation types. This particular J value is calculated based on an established permissible daily exposure, or PDE, the maximum daily dose, or MDD, and the dilution factor used in the sample preparation method of the drug. As a result of the J value calculation, drugs with a larger maximum daily dose, meaning that you would take more of the particular drug product, such as a pill, would require lower element impurity detection limits. And this is one of the reasons for moving to sensitive techniques such as ICP-AES or ICP-MS. So the accessory we're going to discuss today that can be used with ICP-AES is a device called an ultrasonic nebulizer. And the reason it's used as an accessory for ICP-AES is that it enables higher sample transport efficiency versus a standard gas-based pneumatic nebulizer to the ICP plasma. That higher transport efficiency then imparts higher sensitivity and lower detection limits. So this can be helpful for the detection of more difficult elements such as arsenic, cadmium, lead, mercury, and thallium. So this study describes the use of an ultrasonic nebulizer with ICP-AES detection for element impurities in aspirin. Aspirin, of course, is a common drug product, but it's a higher daily dose product than a low dose drug product such as an allergy or sleep aid medicine. An allergy or sleep aid medicine may be just 1 tablet per day, while aspirin may be up to 12 tablets per day. So how does an ultrasonic nebulizer work? Well, we'll spend the next number of slides looking at how the device works and how it's connected to the ICP system. So in place of a regulated gas flow for generation of a liquid sample aerosol, like is used in a pneumatic nebulizer, such as a glass concentric type, liquid is pumped across a quartz plate with an underlying oscillating crystal, and that crystal is what's termed a piezoelectric. A piezoelectric is a crystal with a lattice defect, and you can convert a electrical signal or a potential across the crystal into a mechanical signal as the crystal starts to oscillate or vibrate. The oscillations of the crystal then break up the liquid flow and cause formation of a sample aerosol. This is in lieu of using a gas flow to shear a liquid into a spray. Ultrasonic nebulization is typically up to about 10 times more efficient versus a conventional emetic nebulizer for conversion of the liquid sample into a usable aerosol, hence the reason for its use. So on this slide, I just wanted to give you an idea of the dimensions of the unit. So you see the width, depth, and height numbers both in metric and in English units, and you can see this is really either a benchtop unit, size unit, or a unit that can be conveniently placed on a laboratory cart. So it's not very large, so it won't take up very much space in the lab. The next slide shows a little bit more details. I do want to point out that there are two temperature controllers on the front of the unit, and this is part of the desolvation apparatus to remove any excess water that's generated by the transducer. There's both a heater and a cooler. These controllers are set at the factory and can be adjusted through a range depending upon the liquid types that are introduced, including organics, but this particular application will be aqueous or water-based. The other thing of note I want to point out on this picture is the yellow to orange button. Above it, it says operate. The ultrasonic nebulizer is a one-button operation device. So once it's set up and you have sample pumping in, you'll simply press that yellow button and the aerosol is then initiated. Now, in the back of the unit is where you'll have the connections to connect to your host ICP. So the argon in port in the upper right corner is where you would attach a nebulizer gas line from your nebulizer gas port on the ICP to that connection port. Then after the sample goes through the ultrasonic nebulizer, past the desolvation system, it'll come out a sample out tube, which comes out the sample out slot on the back panel of the unit in the upper left-hand corner. Now, I do want to point out there is a dedicated built-in drain pump in the lower right corner, and that simply serves to remove any excess liquid that's removed by the desolvation system. That particular pump is not used to send sample to the ultrasonic nebulizer. It'll turn on to a set speed once you turn on the power. And finally, a power input module in the back where you would connect the power cord. There's simply a rocker switch on the back that then turns on the power to the unit. But until you press the yellow button on the front, then you would finally then get the aerosol generation. So a schematic, which, and again, I'll show you on the next slide what the setup of the desolvation apparatus looks like. But on the lower left side, you see the transducer. This is the part of the ultrasonic nebulizer which will create the aerosol. There is a conical shaped chamber that the aerosol will then move out into. And where it says argon in is the argon gas flow from the host ICP. In this sense, then, it is acting as a true carrier gas because it's not being used to generate the aerosol, simply to transport it. The piezoelectric crystal in the transducer will do that job. Then once the aerosol is moved along, it goes through a heated J tube or U tube, the two terms are used interchangeably, to both keep the sample in a vapor phase and to start some condensation to remove excess water. Finally, the last bits of water are removed in the condenser, which is denoted in blue. That condenser is Peltier or electrothermally cooled, so there's no need for any type of a recirculating coolant bath to cool the condenser. And then once that's done, what comes out and then moves to the ICP is a relatively dry aerosol of salt particles from the sample. Notice that there are 3 drains that will drain off the excess liquid. And of course, there's a sample import where your pumped sample would come in to the ultrasonic nebulizer. So a little close-up view of the transducer, and this is the part which generates the aerosol in lieu of a standard, say, concentric glass nebulizer. You have a piezoelectric crystal, and mounted on top of it is a quartz plate, and the sample will be pumped across that quartz plate. Another feature of the design of the transducer, you notice the sort of ring design on the back of the metal, and that's actually a heat sink. So as this is in operation, it does warm up. There's a fan that will then blow across that to remove any excess heat to keep it from getting too warm. So if we remove the cover of the ultrasonic nebulizer, you can then see for real the desolvation apparatus. And there is the heated J tube or U tube, and you can see it's partially wrapped with heat cord, but then there's a part that's not wrapped. That will cool down somewhat and act as the first stage of condensation. Then finally, the glass wool will wrap around and will go through the electrothermally cooled region, the condenser, to remove the last vestiges of water before the sample moves on to the ICP. So it's a little bit more difficult to see, but at the bottom, the sample out, denoted in green, you'll attach simply a PVC line to the ground glass joint, and that line will then move out the back of the ultrasonic nebulizer system, and then you would attach that to the ICP torch, and the sample will then move through that line and into the plasma for analysis. So I do want to mention to do the connection between the ultrasonic nebulizer and the host ICP, what you use is what's termed an interface kit. And the interface kit simply is going to consist of some tubing which will bring the nebulizer gas flow from the host ICP to the ultrasonic, and then to transport and conduct the dried sample aerosol to the ICP torch. Finally, there will be usually some type of a torch adapter, and the torch adapter piece that I'll show you in a later picture is actually shown also here. It's the small glass piece in the lower left-hand corner of the picture. That's a 12-5 glass socket, and that's a very common type that would attach to your ICP torch, and onto the stem of that you would attach the PVC tubing that conducts the sample to the torch. So, installation steps, again, going through them in order. First, you would remove the standard nebulizer and spray chamber from the ICP-AES. Connect the nebulizer gas inlet line between the ICP-AES to the USN. Connect the sample outline from the ultrasonic nebulizer or USN to the torch. And then connect the sample outline from an auto sampler to the USN inlet line. So, of course, this can be automated. Connect the power cord to the ultrasonic nebulizer and turn on and wait about 10 minutes for the heater and cooler to stabilize. Start at the ICP. Then usually you would introduce your tune solution. Just press the one button, the operate button, and the samples begin nebulizing. So the overall setup from connecting it and warming it up and actually to start nebulizing the sample only takes about 15 minutes. And no computer control is required. No software installation is needed. So it's very easy to set up. And of course, if you don't need the device, if you want to run other work on your ICP that doesn't require the USN, it's very easy to remove, and then you simply put back the standard nebulizer and spray chamber. So I wanted to show you a few pictures to show you the ultrasonic nebulizer in front of some contemporary ICP systems. And again, you can either place the ultrasonic nebulizer on a benchtop or on a cart and then move it toward the host ICP. In this case, we had the ultrasonic nebulizer on the Agilent 5100 ICP. The current models are now the 5800 and 5900, but the placement strategy would be the same. Here on the Thermo iCap Pro, which is a new system from Thermo Fisher Scientific, again, you see we have the ultrasonic nebulizer placed on a laboratory cart near the system. And the one that we actually used in the aspirin study, the PerkinElmer Avio 500, again on a laboratory cart. There you see I do have the unit on and operating. The yellow button is depressed and on. Also to the right, you see an auto sampler. That's, I believe, an ASX 280 model, and that along with the 560 can be used for automating any sample delivery to the ultrasonic nebulizer. So again, it is a smaller accessory, can be easily placed either on a bench top or laboratory cart. So some details then of the connections. So this shows a close-up of the connection lines coming to the USN, the ultrasonic nebulizer, and then over to the host ICP torch. So there is a gas line that's connecting between the nebulizer gas port and then connects to the back of the ultrasonic nebulizer. So the control of the nebulizer gas flow is still under control of the host computer of the ICP. So that tuning remains the same as you would do with the standard nebulizer. There's simply a sample outline that's called out in blue that then attaches to the ICP torch. A little bit hidden by the auto sampler arm that's pointed out in yellow is the host ICP peristaltic pump. You would normally use that pump just like you would for the standard nebulizer to pump sample from, say, the auto sampler tray to the ultrasonic nebulizer. And finally, of course, the power cord. You would attach that to a power strip or to a wall outlet and simply turn on the rocker switch and turn it on. I will point out again, you might notice to the left-hand side, to the far end of the ultrasonic is that small peristaltic pump. Again, that's simply there to pump out waste liquid to a waste receptacle or condensed liquid. Again, that pump is not used to pump sample to the ultrasonic. And there's a close-up view of a typical torch adapter connection. That's just a 12-5 glass socket adapter mounted in the Tygon tubing. And after you remove your standard nebulizer and spray chamber, that simply will attach on with a clamp. Okay. So the instrumentation that we're going to use in the study that was run is the PerkinElmer Avio 500 ICP-AES, which is a contemporary simultaneous measurement ICP system. The ultrasonic nebulizer model is the Teledyne CETAC U5000 AT+. And for sample preparation of the aspirin, we used a microwave digestion system, in this case, the Mars 6 from CEM. Now, I do want to give everyone just a heads up. I'm going to show a very short video clip. It's only about 10 or 12 seconds. If it doesn't come through on your computer, please don't worry. We'll also upload the presentation on YouTube, and you can then see it on YouTube a little bit later after we have it posted. So what I do want to show you is how to start the aerosol generation. So we'll go ahead and start it. Okay. So I moved over, I depressed the operate button, it turns yellow, and we'll move close up, and then you see the aerosol generated in the spray chamber. Okay. So moving to the next slide, which actually shows a picture of sort of freezing the event that was going on. The aerosol then generates in this conically shaped spray chamber, and there's a sample inlet line that goes up and then brings the sample into the spray chamber, and it flows across the quartz faceplate of the transducer. Once you press that operate button, the aerosol generation begins, and it's then contained in that conically shaped spray chamber. Just to the upper left of the spray chamber, you can see a port, and that's the port where the argon nebulizer gas from the host ICP is coming. In this case, again, it's acting purely as a carrier gas. That gas that's coming up into the upper port of the spray chamber is not used to generate the aerosol. It doesn't shear the liquid as in a concentric pneumatic nebulizer. It simply is acting as a carrier gas, and then the aerosol that's generated is then swept through the desolvation system to remove excess water and then send the dried sample to the ICP. So then in consideration again of USP 232, there's a couple things we want to say about that part of the criteria. First is USP 232 groups the elements by a class rating based on toxicity. So first, there are class 1 and 2A elements which must be measured, and the class 1 elements are the most toxic. The big four are cadmium, lead, arsenic, and mercury. Okay. The class 2B elements must be measured if added to the drug product generation process. Class 3 elements are of lower toxicity via oral administration, but require measurement if the drug product is given by inhalation or parenteral route, such as injection or intravenous. There are a total of 24 elements, and we'll show all of those except osmium, which is a gas, in some of the upcoming tables. But this is one important part of the USP 232. The other is the maximum daily exposure limits. And in this case, what we've listed in the next two slides are the maximum oral daily exposures as defined in USP 232. So first here, and I had to, at least so you could see it more easily, split the list into two tables. But notice the big four again, the four class 1 elements, cadmium, lead, arsenic, and mercury, with some of the lower maximum oral daily exposures, and also thallium, a 2B, with a lower exposure limit of 8 micrograms per day. So then moving on to the other elements, the class 2B and class 3 elements, then you see the maximum oral daily exposure limits then increasing. So those are of not as high a concern as the class 1 and class 2A. So for sample preparation, a half-gram sample of the aspirin with multi-element spike was added to each digestion vessel, and the reagents used were reagent-grade nitric acid concentrated and reagent-grade HCl also concentrated. 5 mils and 1 mil were added, and the vessels were left uncapped for 10 minutes to allow any initial gases to vent prior to sealing the vessels and then digesting them by a microwave digestion program. Again, this was run on the CEMR6, and the digestion program is listed below. Very straightforward program for 30 minutes. So after digestion, the samples are then diluted with deionized water, and the final dilution was 100-fold. With that dilution factor and a maximum daily dose of 4.32 grams, one aspirin tablet that we used was 0.36 grams. The maximum dose is 12 tablets per day. The J values could then be calculated, and those are listed in the next two slides in units of milligrams per liter. So USP 233, the other part of the criteria, describes calibration and verification of the calibration. And per that protocol, you have to run a reagent blank, a 0.5 J standard, and a 1.5 J standard for calibration. So on the next slide, you can see the calculated J values. And again, the class 1 elements, cadmium, lead, arsenic, mercury, have the lower J values. And these values are all in milligrams per liter. If you multiply by 1,000, they would be in part per billion. But again, as you move from the class 1 and 2A elements up to the class 3, you can see these J values then increase. So calibration and reagent addition. So the ICP was calibrated using standards that were matrix matched to the acid concentrations of the digested samples. And you saw in the previous slide the nitric acid and HCl mix that was used. After dilution, it gets to about 10% of each. An internal standard solution of 50 ppb or microgram per liter yttrium was added to all samples and standards using the mixing tea. Now, an important point in the study that was done is that samples for the class 1 elements, including mercury, 2A elements, and thallium, were digested and analyzed separately from the class 2B and class 3. For the class 1 elements, and particularly with regards to mercury, The reagent L-cysteine, which is a thiol-containing amino acid, was added to the adjusted samples to assist element transport of mercury through the ultrasonic nebulizer. Mercury is a memory-prone element, and L-cysteine, since it contains sulfur, is very good at complexing the mercury and improving the transport through the glassware of the ultrasonic nebulizer. The L-cysteine was also added to the internal standard solution, so the final concentration after sample mixing was about 3 milligrams per mil of L-cysteine. Nitric acid does rapidly oxidize it, so the internal standard solution that was teed in was prepared in 0.07 molar HCl, which is not oxidizing as much as nitric acid. I did want to show you the structure of L-cysteine. So just as a reminder, this is a amino acid, and off the central carbon, you have the hydrogen, the amino group, the carboxylic acid group, but the R group has the thiol functional group, the SH group, also known as a sulfhydryl group, and this acts very well to complex the mercury and help its transport through the system. So some additional notes on the aspirin tablets. These did not contain any silicon dioxide or titanium dioxide, so hydrofluoric acid was not needed in the digestion procedure. If hydrofluoric acid was required, then you would have to have a neutralization of the residual hydrofluoric acid, usually done with boric acid, before introduction to any glass components. Of course, the components in the ultrasonic nebulizer, as I mentioned, are quartz, so hydrofluoric acid would attack that, as it would any glass components such as a glass concentric nebulizer or a glass spray chamber. But that was not a concern in this application. Emission line selection. All elements required by the USP 232, and there's a total of 23 that we measured except for osmium, and other elements potentially in the aspirin sample such as calcium, sodium, silicon, magnesium, were run individually to check for spectral interferences. Of course, when possible, you look to use emission lines free of the interferences. Otherwise, techniques such as multi-component spectral fitting on the Perkin-Elmer system, or MSF, or element correction factors were used. In addition, an interference check solution was measured during the sample run to verify that the spectral correction techniques were working properly. So a review of the operating conditions, and this is a comparison running the ICP emission system with the standard nebulizer, which was a glass concentric type, a Meinhard K, versus the U5000 AT+ ultrasonic nebulizer. And overall, the conditions are very similar. A couple of differences I do want to point out is the nebulizer gas is a little bit lower, 0.7 to 0.62, very easily adjusted through the computer software. And the cassette position, essentially the position of the torch, was a little bit lower with the USN, set at -5. But there you see the rest of the conditions, integration times, peak area, 3 points per peak, and 3 replicates for each measurement. So this is just a list of the elements and wavelengths along with the plasma view chosen, again, for best performance, best signal, and least interference. So you see the list here. There are some elements that were a little bit better under radial conditions, and you can see those: palladium, rhodium, some others here: ruthenium, lithium, antimony, barium, copper, and chromium, especially as you move to some of the higher concentration J values. You didn't want to saturate the system by using perhaps the highest sensitivity wavelength or moving to axial viewing. So some example spectra, and these are very informative. This first one for lead, which is, of course, a class 1 element, one of the big 4. This is an overlay of the emission spectra at 1J, 0.01 milligram per liter, or 10 ppb, We can just see a little bit of a peak with the standard nebulizer, which is in black, but we see a very distinct peak in red from the ultrasonic nebulizer. In addition, I want to point out you do have a significantly reduced background, and that's probably from less injected water being introduced to the ICP because of the desolvation system of the USN. So the 10 ppb lead very easily detected when the ultrasonic nebulizer is used. Next, arsenic, another class 1 element, this time at 30 ppb or 1J. Again, we can see this with the standard nebulizer. There is a peak, but a much more pronounced and stronger peak with the ultrasonic nebulizer. That's, of course, depicted in red. And then an important element of interest of mercury, where we did the sample modification with the L-cysteine. Very good peak at the 253 wavelength, and really more difficult to see with the standard nebulizer, and that's at 60 part per billion. And finally, one of note, and this is a class 2B element, but the J value is quite low. It's at 0.016 ppm or 16 ppb for thallium, and really couldn't detect a peak with the standard nebulizer, but with the ultrasonic nebulizer in red, we could very easily discern a peak at the main wavelength of 190.8 for thallium. So without the ultrasonic nebulizer, really couldn't do this 1J measurement of thallium with the standard nebulizer setup. So in addition to the calibration procedure defined as the blank 0.5J and 1.5J, there are also criteria defined in USP 233 for validating the quantitative procedures. And these 4 criteria are listed in the table, and we'll go through these carefully. First one is accuracy. So after calibration, spike recoveries at half J, J, and 1.5J must be between 70 and 150%. Repeatability. The RSDs, percent RSDs of measurements of 6 independent samples spiked at the 1J value must be less than 20%. Then ruggedness. 6 solutions must be analyzed on different days, with different instruments, or with different analysts. And the RSDs of the 12 measurements pooled over those measurements must be less than 25%. In these tests that we performed, we simply ran the samples on a different day. And then finally, system suitability. The difference in the results of the high calibration standard 1.5J measured at the beginning and the end of a batch must be less than 20%. So let's take a look at the results. So first for accuracy, and we looked at 0.5J and 1.5J spike recoveries in the aspirin. The black top line is 150% threshold. The gray bottom line is the 70%. And you can see here at the 0.5J and the 1.5J, the recoveries come right in line. They range from about 82 to 105%. So the ultrasonic nebulizer does meet the criteria for accuracy. Next, repeatability. Again, the percent RSDs of 6 independent samples spiked at 1J. The RSDs must be less than 20%. All of them are well below 10%, with the highest arsenic being about maybe 7 or 8%, but well below the criteria established. Then ruggedness. The percent RSDs of 6 independent samples analyzed over 2 days. So then 6 times 2 or 12 measurements pooled, and the percent RSDs must be under 25%. Again, all well below that. Most of them are under 5%. And finally, system suitability, the analysis of the 1.5J standard at the beginning and the end of the analytical run. The difference in the results must be less than 20%. Here they're ranging in a range either plus or minus absolute value between 0.4 and 8.4%, so certainly well within the limit of 20%. So in summary, all of the criteria required by USP 233 were met when we used the U5000 AT plus ultrasonic nebulizer with ICP-AES detection of trace elements in aspirin, a higher daily dose drug product. The U5000 AT plus USN enables enhanced analyte sensitivity and lowers background emission, improving the ICP-AES measurement of more difficult elements in this example of a higher daily dose drug product. So again, some specific benefits. Again, the enhanced detection of some of the difficult class 1 elements, such as lead, arsenic, and mercury, as we showed in the spectra, and the class 2B element thallium. Usually lower background emission due to less injected water vapor going into the plasma because of the desolvation system of the ultrasonic nebulizer. As we explained, the setup of the U5000 AT Plus with the interface kit is fast and easy. Convenient placement on the laboratory cart or benchtop. In the small video clip, you saw just a one-button operation. You simply press the yellow operate button and the aerosol is initiated. No computer control is required. No software installation is needed. And simple connection to an auto sampler, such as an ASX 280 or 560 from CETAC for automated sample introduction. So I just wanted to end with some part numbers for your reference. Top level part numbers for the ultrasonic nebulizer, there are two. There is one for a 115 volt version and for a 220 volt version, depending upon the voltage you are set up to use. And those two numbers are listed there. The only difference is the A is for the 115 volt and the B version is for the 220 volt. Of course, I did mention and I did show a picture of a interface kit, which you use to then connect the ultrasonic nebulizer to the host ICP. We have interface kits for all models, and these are some of examples of the common models that the ultrasonic nebulizer is sold on: Agilent, Analytic Jena, Perkin-Elmer, Shimadzu, Spectro, Teledyne Lehman, Thermo Fisher. You would simply reference one of those SP spare part numbers with an ultrasonic nebulizer order, and that kit would then enable you to make the connections. One kit is provided at no charge, which with each U5000 AT plus USN. So in acknowledgement, I want to give special thanks to Mary Jo Menke-Wright for her work in the sample preparation, method development, data collection, and outline text for this application. There was a lot of work that did go on in the method development, in certainly the use of the L-cysteine to improve the mercury numbers, and for checking for all of the interferences that can occur in a relatively complex matrix after the aspirin samples are digested. And where to go for more information. Service support and sales support both have email addresses that you can email to if you have questions regarding a ultrasonic nebulizer you may have, or if you're interested in acquiring one. Technical support, and for any questions regarding the webinar, certainly you can send them to myself at fred.smith@teledyne.com, or my colleague Paula Duscott at paula.duscott@teledyne.com. Of course, there's more information on our website. The first link gives a broad overview of the ultrasonic nebulizer, the U5000 AT Plus, and the link just below is the full application note with additional details on the application I described in the slides today. So again, this webinar, the slide presentation, will be available on YouTube, and you can go through that at your convenience. And If you have any questions, please send them to myself again at fred.smith@teledyne.com. And again, thank you, Shelley, for setup of the webinar today, and thank you everyone for attending. And again, if you have questions, please email to the email address shown on the screen. Thank you again.